See, what is the surface energy? Now all molecules pull inside the liquid. Now the molecule from bottom to taken in the top position, there is a work done, and this work done, it is stored in the form of potential energy, and this potential energy, it is called as surface energy. Then this surface energy having SI unit joule, and its dimension is like the energy, it is L2 m1 T minus 2, and this is the dimension of surface energy. These are the surface tension and surface energy. Relation between surface tension and surface energy. Now consider the frame PQRS. Consider this is rectangular frame PQRS. This frame dipped in soap solution, there are two films are formed, and if we increase, this is the movable, RS is movable. If we increase this area, we get there is a force acting on this film, and the surface tension, force of surface tension is equal to, we know surface tension T is equal to F upon L. Therefore, force of surface tension, it is T into L. This dipped in soap solution. Therefore, there are two films, and the force due to surface tension, it is T into 2L. Two factor, it is due to the soap bubbles or soap solution having two surfaces. Therefore, we can write F is equal to T into twice L. Now, see, there is another equal and opposite force by Newton's law, and which is also equal. Therefore, we can write it is F dash is equal to T into 2L. Now, there is a work done, and this work done is nothing but dW. dW is equal to, that is here we pull this wire towards the left and we get the thickness of through distance dx, we get F dash dx. Therefore, dW is equal to F dash, value of F dash is T into 2L dx. Now, this is the area, this is the length, this is the thickness. Therefore, 2L dx, it is called as change in area, increase in area. Substitute this value in above equation, we get dW is equal to T into dA. That is T is equal to dW divided by dA. This dW, it is called as surface energy. This is the surface energy, that is dW is equal to T into dA. This is called as surface, this is stored in the form of fluid, or it is called as surface energy. This surface energy is equal to T into dA, which is the relation between surface tension and surface energy. Now, we see the angle of contact. Next concept, angle of contact. See, suppose we consider kerosene or impure water. The upper surface, face surface of liquid, it is concave. Why? It is said later. Now, there is another liquid, for example, mercury. See, here we consider the two examples of fluid. Here we consider kerosene or impure water, here we consider a mercury. In case of kerosene, the free surface of liquid, it is concave. Now, in case of mercury, it is convex. Now, suppose we draw the tangent to this free surface and the point of contact here, solid liquid, it is the theta, and this theta, it is called as angle of contact. Angle of contact. Now, in this case, this is the free surface of this mercury. Again, we draw the tangent here. This angle is angle of contact. Then we can say that we can define this angle of contact. See, this is the angle between. This is the angle between tangent to the free surface and the point in contact with solid and liquid. This is called as angle of contact. Now, the angle of contact or this angle of contact for kerosene or impure water, the angle is acute here, that is less than 90. See, suppose this angle is 90, but it is less than 90, this angle is acute here. Now, this angle is greater than 90, the angle is obtuse here. See, in case of the kerosene, that is which weights, partly weights the solid, the angle is acute, and in case of mercury, which does not weight the solid, or it is called as the angle is obtuse. Now, we see the explanation of angle of contact. Explanation of angle of contact. Why there is angle acute? Why there is angle obtuse? Now, see, suppose this is the point, this is the solid surface, this is the liquid surface. Now, this is liquid and this is solid surface, contact with solid. Now, this is suppose molecule A. In first case, suppose we consider here impure water or kerosene. Now, in this case, we know there are two forces, cohesive force and adhesive force. In case of the fluid or liquid which weights, partly weights the solid, the adhesive force or this adhesive force is greater. Suppose it is AP, it is greater than this cohesive force. The resultant lie in the solid, Again draw the 90 degree here, and this angle is 90. Suppose we draw the parallelogram here, and this angle is acute here. Now, this is the drop, or this molecule scripts in the upward direction, and this surface is concave here. Now, suppose in case of mercury, again consider this is solid surface, this is liquid surface. Suppose this is molecule A. In this case, again the cohesive force in case of mercury, it is shorter or it is less than this cohesive force. Again, this resultant, it is in the liquid, and this molecule, suppose we draw the 90 degree resultant here, and this molecule skips in the downward direction. This is the convex surface. In case of mercury, the upper surface is convex due to material property, that is due to cohesive force and adhesive force. In case of kerosene or impure water, the resultant force or this cohesive force is greater. In case of mercury, this cohesive force is lesser. Therefore, there is a concave surface, there is a convex surface. In case of pure water, suppose this is molecule A, this is solid, this is liquid. In pure water, the cohesive force, it is equal to this cohesive force, and the resultant, it is lies along this, and it is perpendicular distance, and the angle of contact, it is 0 for the pure water. From this we can say that angle of contact for kerosene, it is acute, angle of contact for mercury, it is obtuse, for pure water it is 0. Now we see the shape of liquid drop. Shape of liquid drop. See, suppose this is the solid surface, then see this is the liquid drop, this is the tangent, this is the T1, force of surface tension between solid and liquid, this is the force of surface tension between solid and air, and this is the force of surface tension between liquid and air. Now this is through angle theta, this angle is acute. Now suppose we consider here there are two components of T3, this vertical component is T3 sin theta, and this horizontal component, it is T3 cos theta. This is for angle acute. Suppose we consider a mercury drop, we know mercury drop, then this angle is obtuse here, again this is the T1 force, this is T2 force, this is T3 force, again it is T3 cos theta. The situation is same, here we consider the impure water or kerosene, here we consider the mercury. Now see this figure, in this figure T1 is the force of surface tension due to solid and liquid, T2 is the force of surface tension due to solid and air, T3 is the force of surface tension between liquid and air. Now the T3 having two components, the horizontal component, it is T3 cos theta. Now from vector geometry we can say this T1 and T3 are in the same direction, therefore we can write T1 plus T3 cos theta, which is equal to T2. Again we get T2 minus T1 is equal to T3 cos theta, and cos theta is equal to T2 minus T1 divided by T3. Now this theta is angle of contact. Now consider the first case, suppose T2 is greater than T1. Now this T2, value of T2, it is greater than T1, then the cos theta is positive. It is positive and theta is acute. Theta is acute. Now consider the second case, suppose T2 is less than T1, cos theta is negative and theta is obtuse. Now suppose we consider T2 minus T1 is equal to T3, cos theta is equal to 1, and the drop is not found, or we can say there is a, no, it is impossible, and in another case the drop is not formed. Now we consider capillary action. Capillarity or capillary action. Capillary action or capillarity. Then see, in case of kerosene or impure water, suppose this is the kerosene that is partly wet the solid, suppose the capillary dip in this liquid, the liquid rises in this capillary. Now suppose we consider the mercury here. Suppose a capillary dipped in mercury. In this case, there is a decrease in height, that is we can say there is a fall of mercury level, or the height it is fall. Here height increases, height decreases. Therefore we can say that the phenomena of rise of liquid or fall of liquid inside this capillary tube, it is called as capillary action. See, here there is a rise of liquid inside the capillary. Here there is a fall of liquid level in the capillary. In both cases, the liquid level rises or liquid level drops. The phenomena of rise of liquid inside the capillary and fall of liquid level inside the capillary, it is called as capillary action. In case of water, there is rise of liquid in a capillary. In case of mercury, there is a fall of liquid level. Now the capillary, what is the capillary? This is the small, or this is the glass tube having very small fine bore. It is called as capillary. Now we consider the pressure action here. There are different examples of capillary action or capillarity, that is rock soaks the water. Then suppose there are trees, the water, mineral salt water reaches up to top, it is due to capillary action. Now we consider the pressure. Now in case of, suppose we consider here, there is a capillary rise. Suppose consider this is point A, this is point B, this is point C, and this is point D. Now this is the, suppose we consider concave surface, that is which partly wets or wholly wets the solid, the upper surface, free surface is concave. Now here there is a plane surface, that is pressure at C is equal to pressure at D. Now here pressure at A is equal to pressure at C, that is this is the point in atmospheric pressure, this is the point in atmospheric pressure. Thus we can say that pressure at A is equal to pressure at C. But in case of, that is here pressure created at point D and at point B, that is pressure at point D, it is greater than pressure at point B. When the liquid, for equilibrium, liquid rises inside the capillary until the pressure at point D is equal to pressure at point B, and there is a rise of liquid level inside the capillary, and the action is capillary action. Now we see the expression for capillary rise. Capillary rise or fall. Now in case of, suppose in pressure method we consider this is the concave surface, again this is the, suppose this is the radius of this capillary tube, this is the radius of curvature. Now this angle, suppose we draw the tangent here, this angle is theta. Again due to geometry this angle is also theta. Now from figure we can say that this is the force of surface tension, and the excess pressure is equal to, we know the excess pressure is equal to, from Laplace law it is 2T divided by R. Now from figure we can say that it is R is equal to cos theta is equal to, cos theta is equal to, no, cos theta is R divided by r. This is the coincide side, this is the hypothesis. Therefore, cos theta is equal to r divided by r. Therefore, r is equal to, capital R is equal to this r divided by cos theta. Here we take capital R. Substitute the value here, that is P is equal to 2t. Substitute the value of r here, r divided by cos theta. That is P is equal to 2t cos theta. 2t cos theta divided by this r. Now this P is pressure, and pressure is nothing but it is H rho g. That is, H is the height of mercury, rho is the density, g is the acceleration due to gravity. We can write here 2t cos theta divided by r, and height is equal to, H is equal to 2t cos theta divided by r rho g. This is the height of this, or rise of the liquid level in the capillary tube. Now from this we can write the surface tension. T is equal to H r rho g divided by 2 cos theta. This is the formula for surface tension, where T is the surface tension, H is the height, that is this height, r is the radius of capillary tube, rho is the density of liquid, g is acceleration due to gravity, theta is angle of contact. This is the capillary rise or fall due to simple method, pressure method. Now we see the next method. Using forces. Suppose this is the force, this is the upper surface, it is circular, this is the force of surface tension. There are the weight, it is in the downward direction, this is the vertical component of surface tension, it is Fv cos theta. Horizontal components are cancelled with each other, and this angle is theta here. Now this vertical component of these, they are added, and we get, they are added and multiplied by this length of this circumference. Thus we can say that it is surface tension here, that is force is equal to 2t. T is equal to F upon L, T is equal to F upon L, and this F is equal to T into 2 pi r cos theta. This is the first equation. Now this is the vertical component, it is exactly equal to, this is the downward component, and mg is equal to, again we can write here m is equal to mass, rho is equal to mass upon volume. Mass is equal to volume into density. Volume is equal to this volume, it is pi r square h into rho. Therefore, substitute the value of m here, we get pi r square h rho into g. These two forces are equal and opposite, therefore we can equate these two equations. T is equal to T 2 pi r cos theta into pi r square h rho g. Then what is the expression for height or tension? We get here, see, r, pi, and T is equal to r h rho g divided by 2t 2 cos theta. This is the expression for surface tension. This is the expression for surface tension. Now there is excess pressure. Suppose we consider a soap bubble, excess pressure Laplace theory, that is we can say suppose this is the drop and Pi is the initial pressure of and Po it is the outside pressure. This is the outside pressure, the thickness is dr. Therefore, Po minus Pi it is the or Pi minus Po it is the excess pressure and which it is equal to we can find here and it is 2T divided by R for drop and Pi minus Po 4T divided by R for bubble. This is for surface tension or excess pressure.